And we know how LEDs produce light now, and we know how to quantify the efficiency of that light production. Now, how do we make LEDs that will produce light in a range of colors? Why is this important? Well, for example, if you want to make a display, you need LEDs of different colors. What colors do you need? You need red, green, and blue. Oops. Why these colors? Well, these are the colors, the primary colors of light. So if you mix these colors in different weighted combinations, you can get all the colors in the visible spectrum. So we want to know how to make LEDs that will produce those colors. Now we know that the energy of the photons that are produced from the LED is close to the band gap energy of the semiconductor. So that means that if we want to change the energy of the photons and therefore change its wavelength, we need to change or need to be able to engineer and change the semiconductor band gap. So here's a figure relating the band gap energies of different types of materials that span the visible wavelength. This figure is from Fundamentals of Photonics by Saleh and Teish. So it's not in your textbook. That's why I'm showing it to you in this video. So the visible wavelength is at the in this spectrum here, given by the different colors. So you can see different material combinations. For example, in this section here, these are the various combinations of this one is aluminum gallium arsenide, and by changing the ratio of gallium arsenide and aluminum, you can cover this wavelength range. This is for a direct band gap. You still can make a semiconductor in this range, but this is an indirect band gap semiconductor, so we don't want that. This is for gallium arsenic phosphide. This one is indium gallium phosphide, and you can see that they're covering the red to yellow wavelengths using those color combinations. Getting out to green here, if you look at indium aluminum phosphide, one of the innovations, in displays, which is why we didn't always have these LED displays, is down at these shorter wavelengths, because we need red, green, and blue, right? So we can produce red and up to green using semiconductors based on gallium, but we couldn't get these blue wavelengths until relatively recently, about 20 years ago, and that was using this gallium nitride combination of semiconductor materials. So you can see that spans the blue to violet wavelength range, and it was hard to get these materials to work together because of the difficulty of putting gallium and nitride together reliably. So the engineer that figured out how to do this, Shuji Nakamura, won the Nobel Prize for being able to make gallium nitride based semiconductors. This was the Nobel Prize in 2014. But anyway, you can see that we have this semiconductor materials library that you can use to make LEDs that produce photons that span this visible wavelength range.